Hey guys, it's Miss Rainey. We're back with Chemical Foundations Part 3, and we're going to be learning about the metric system and conversions from one unit to another, dimensional analysis, also known as factor label, temperature units and how to convert between them, and density. Are you ready? Let's get started. Okay, we're starting here with the metric system and converting between units within the metric system and within the English or imperial system. The metric system is built on a base 10 system where the base unit is a meter or a liter or a gram, and then we add a prefix to that meter, liter, or gram to say how big it is. So we can add a tera to a meter, so a terameter is 1 times 10 to the 12th meters. Or we can add a kilo to a gram, so a kilogram is 1 times 10 to the third, or 1,000 grams. We can go the opposite direction and smaller so that we can have 100 centiliters is 1 liter, or a million micrograms is 1 gram. So this is how big or small they get from the base unit. And then we have some common English conversion factors over here, and these aren't to memorize, they're just kind of to remember that they exist. You won't have to memorize them, but you will have to reference them. Okay, so dimensional analysis, or factor label, is a method of converting a measurement in one unit to another unit. So it uses a conversion factor, which is created from an equivalency that's equal to 1. So just for a second, let's imagine this fraction, 1 over 1. And we know 1 over 1 is equal to 1. What if this was 12 over 12? Well, our math teaches us that 12 divided by 12 is the same as 1 over 1, so 12 divided by 12 is 1. What if it were 12 inches over 12 inches? Well, that's also equal to 1 because the 12's both cancel and the inches both cancel, so this is equal to 1. So then, what if I made this, instead of 12 inches over 12 inches, what if I turned it into 12 inches over 1 foot? Well, guess what? That is also equal to 1 because 12 inches have the same equivalency as 1 foot, so both of those cancel out. So if we had a conversion factor like 2.54 centimeters is equal to an inch, we could have 2.54 centimeters over an inch, which equals 1, or 1 inch over 2.54 centimeters, and that also equals 1 because the number on the numerator and the number in the denominator are equivalent to each other. So when we're doing dimensional analysis or factor label, we multiply a quantity by a conversion factor so the undesired unit cancels. So we take 31.8 centimeters and we want to turn it into inches. So we're going to use the conversion factor with inches on top and centimeters on bottom. That way the centimeter will cancel with the centimeter, 1 in the numerator and 1 in the denominator. And 31.8 times 1 divided by 2.54 is 12.5. And so then our unit that's left over is inches. So we have the same equivalent distance, 31.8 centimeters is 12.5 inches, but a different number in front because we have a different unit represented. So here's our first question. What is the weight of a 2.3 pound pineapple in milligrams? So I personally don't have off the top of my head the number of pounds there are in a milligram, but what I see in my conversion is the number of ounces there are in a pound and the number of grams there are in a pound. Seems to me that grams in a pound is going to be my more useful conversion because I can easily go from grams to milligrams. So I'm going to start with 2.3 pounds for my pineapple. My conversion factor is going to be 454 grams in a pound. I'm going to put the pound on the bottom, so the numerator pound will cancel with the denominator pound, and the grams on the top. Then I'm going to put the equivalent numbers with those, 454 with the grams, and 1 with the pounds. That will cancel my pounds to grams. But I'm not quite done because I'm looking for the milligrams of a 2.3 pound pineapple. So I'll go one more conversion factor, grams to milligrams. If we recall from our metric system prefixes, a base unit of a gram has 1,000 milliunits in it, so 1,000 milligrams in a gram. If we watch our units, they cancel. Pounds, numerator and denominator cancel. Grams, numerator and denominator cancel. As far as our numbers, we'll have 2.3 times 454 times 1,000 divided by 1, and I get 1,044,200 milligrams. Okay, now if we remember a little bit about our significant figures, 1,044,200 has about, let's see, 1, 2, 3, 4, 5 significant figures, but the number 2.3 only has 2 significant figures. So I'm going to have to round this number, 1,044,200, to 2 significant figures. So if I round that to just plain 1 million, that's, hold on, right there without the decimal point, that's only 1 significant figure. And if I put the decimal point at the end, that's 7 significant figures, but I need 2. So this is an example of something that would require scientific notation in order to get my 2 significant figures. That would be 1.0 times 10 to the 6th milligrams. All right, let's try another one. The volume of a solid is measured by water displacement. When the solid is placed in a graduated cylinder containing 20 milliliters of water, the water level rises to 23.2 milliliters. What's the volume of the solid in cubic inches? So I have a graduated cylinder, bear with my picture here, and it has some water in it at 20 milliliters. And then when I put a solid in it, whatever that solid happens to be, the water level goes up to 23.2. So that means that the volume of the solid, and if I use my correct significant figures here, sorry, is 3.2 milliliters. So let's convert those 3.2 milliliters to cubic inches, which is what the question is asking us, using our dimensional analysis. 3.2 milliliters, and then the conversions at the top say that a milliliter and a cubic centimeter are the exact same thing. 1 milliliter is equal to 1 centimeter cubed. But we don't want cubic centimeters, we want cubic inches, so I have to do another one that says centimeters to inches, and I've got that up here somewhere, right there. 1 inch is 2.54 centimeters. But there's a trick here, because this is asking for cubic inches, and I've just got regular inches. There's no cube up here, and there's no cube down there. So let's imagine a cube. Okay, I'm going to draw my cube the best I can, not the best cube drawer. And let's just pretend this cube was 1 inch on each side. 1 inch here, 1 inch there, 1 inch there. 1 times 1 times 1 is 1 cubic inch. So that's a 1 cubic inch cube. Let me label that. 1 inch cubed. Okay, so let's think about the centimeters then. As far as the centimeters concerned, that would be 2.54 centimeters on this side, and 2.54 centimeters on that side, and 2.54 centimeters on this side. So this cube, which is 1 times 1 times 1, is the same as 2.54 times 2.54 times 2.54. In other words, 2.54 cubed centimeters cubed are in 1 inch cubed. So it's not just 2.54, it's 2.54 cubed, which if you type that in your calculator gives you 16.387 centimeters cubed per inch cubed. So we can take any of these conversions and make it a cube if we cube everything. 2.2 cubic pounds are in 1 cubic kilogram. We would have to cube everything. But we're not looking at pounds and kilograms, we're looking at inches and centimeters. So let's see. Our milliliters will cancel. Our cubic centimeters will now cancel. We are left with cubic inches. That is 3.2 times 1 divided by 16.387 gives me 0.1 1953 inches cubed. When I'm looking for significant figures, I have, how many is this here? 2 significant figures in my 3.2. So I want 2 significant figures, but that 5 rounds up. So I'm going to have to write it up at the top here. 0.20 inches cubed. There we go. Okay, it looks like I have one more factor label problem here. A car is driving down a residential street at 30 miles an hour. How many feet is that in car traveling every second? So 30 miles per hour. And we are looking for feet per second. So we'll start here. 30 miles per 1 hour. So this unit has a unit on top and a unit on bottom. We're going to have to convert both. Let's see. Up there I've got feet to miles. It says 5,280 feet per mile. I'll put miles on the bottom to cancel it out, feet on the top, and then the equivalent numbers in each one. That will end up canceling my miles for me and giving me feet, which is one of the units I'm looking for. But the other unit is hours to seconds, or time. So for my next unit, I want to convert hours and cancel out the hours. It's starting in the denominator, so I'm going to put hours in the numerator so that it will cancel out. And you may know hours to seconds, but it's easier for me to go hours to minutes because I know an hour has 60 minutes in it. And the hours have canceled. But I don't actually want minutes, I want seconds. So I'm going to do another one. Since minutes is currently on the denominator, I will cancel it by putting it on the numerator and seconds on the bottom. And 1 minute has 60 seconds inside of it. And so, therefore, I'm left with seconds that doesn't cancel. So my overall unit is feet on the top on the numerator, seconds on the denominator. When I am typing this in the calculator, I have 30 times 5280 divided by 60 divided by 60. The 60s are on the bottom. I end up with 44 feet per second. So even if you're traveling relatively slowly at 30 miles an hour, every single second you're driving 44 feet. One more thing, if I'm thinking of significant figures, 30 with no decimal point has only one significant figure. So to round this to one significant figure, this would be 40 feet per second. 30 miles an hour is approximately 40 feet per second. All right, now let's look at density. Density is an object's mass compared to or divided by its volume. Density is mass divided by volume. So if a student was trying to determine the density of an unknown liquid, the student placed a graduated cylinder on a balance and determined the graduated cylinder's weight is 12.32 grams. That's the mass of the cylinder is 12.32 grams. The student then places 20.2 milliliters of liquid in the cylinder, so volume of liquid is 20.2 milliliters, and then places it on the balance again, and this time the balance reads 29.73 grams. The mass of the cylinder and liquid is equal to 29.73 grams. So to find the mass of the liquid by itself, I'm going to subtract these two numbers. The 29.73 minus the 12.32 gives me 17.41 grams for the mass of the liquid. And then my density is just taking my mass divided by my volume. So my density is 17.41 grams divided by 20.2 milliliters, and I end up with 0.862 grams per milliliter. And now the question says, what is the unknown liquid? The closest to 0.862 looks like it is toluene. So my unknown liquid is toluene. All right, next, a student would like to collect 350 grams of diethyl ether. Here that is in my little chart. What size beaker should be used? Okay, 350 grams. Grams is a unit of mass. What size beaker? Well, beakers come in like 50 milliliters or 100 milliliters. In other words, we're looking for the volume of the beaker. That is what I'm looking for. And I have the mass of the ether. I also have the density of the ether up in that chart. So if I have the density and I have the mass and I'm looking for the volume, I can rearrange that formula to volume is equal to mass over density. So then I'm going to take my mass, which is 350 grams, divided by my density, which is 0.714 grams per milliliter. It says grams per centimeter cubed, but grams per milliliter is the same thing. And I will divide those, and I end up with 490 milliliters would be the volume of 350 grams of diethyl ether. There's a trick though. It didn't ask for what was the volume of the diethyl ether. It says what was the size of the beaker. A beaker doesn't come in sizes like 490 milliliters. The beaker will come in pretty common sizes of something like maybe 500 milliliters, or maybe a 1 liter beaker would hold 490 milliliters of liquid. All right, here is my last density problem. What is the mass of 1.25 quarts of isopropyl alcohol? So what is the mass? Means I am looking for the mass. This is my question mark. Of 1.25 quarts. That is a volume of isopropyl alcohol. And there's my density of my isopropyl alcohol. So here's my problem. My volume is in quarts. My density is in grams per centimeter cubed or grams per milliliter. And I'm not sure exactly how many quarts there are in a milliliter. So I'm going to need to go back to my other chart and look at my conversion factors. So let's try this again. What is the mass of 1.25 quarts? And then the density of isopropyl alcohol is 0.785 grams per milliliter, or grams per centimeter cubed, whichever works easier for your problem. Okay, so I'm going to have to convert quarts to milliliters. Let's see, quarts to milliliters. I see quarts to pints. I see pints to cups. I see milliliter to cubic centimeter, quarts to gallons. Which one of these would be the most useful? So I can take quarts and take it to gallons. I can take gallons and change it to liters. And I can take liters and change it to milliliters. So let's go ahead and use these. Quarts to gallons, gallons to liters, liters to milliliters. So this is 1.25 quarts. There are 4 quarts and 1 gallon. 1 gallon is 3.79 liters, and 1 liter is 1,000 milliliters. I'm getting those off of my conversion charts on my other page. So I will multiply 1.25 divided by 4 times 3.79 times 1,000, and I end up with 1184 milliliters of isopropyl alcohol. All right, so my volume is 1184 milliliters, and I'm looking for a mass. If we know that density is mass divided by volume, then mass must be density times volume. So here I'm going to take my density, 0.785 grams per milliliter, and my volume, 1184 milliliters. Multiply those two numbers together, and I end up with 929.73 grams. Since I only want 3 significant figures, I'm going to round this, and the 7 rounds up. So I end up with 930 with a decimal point to give me 3 sig figs grams. All right. My next is temperature units, and so we're just going to convert between temperature units. I've got some temperature scales. We've got Fahrenheit, which you're hardly ever going to see in a science class, but just here for this beginning. I've got Celsius, which you're going to see most often, and then Kelvin when we are trying to use gas law math problems. So water boils at 212 degrees Fahrenheit, which is the same thing as 100 degrees Celsius, which is the same thing as 373 Kelvin. If it's room temperature, this room is pretty comfortable. That would be about 77 Fahrenheit, which to me is actually a little bit warm. 25 Celsius is considered room temperature, and 298 Kelvin. Water freezes at 32 Fahrenheit, or 0 Celsius, or 273 Kelvin. And then absolute zero, which is the coldest theoretical temperature possible, negative 459 F, so negative 460 F should not exist. Negative 273 Celsius, or 0 Kelvin, which is actually where the Kelvin scale comes from. It puts absolute zero as 0. So our thermometers and temperature probes will always measure temperature in Celsius. Here's our conversions. If we want to go to Kelvin, we're just going to take our Celsius and add 273. If we want to go to Fahrenheit, which you're hardly ever going to do, but we will for our dual credit class, we'll take 1.8 times the Celsius plus 32. So here's our last problem. In July of 2022, the town of Coningsby in England recorded a temperature of 40.3 degrees Celsius. That's the highest ever recorded in the United Kingdom. How hot is that in Kelvin, and how hot is that in Fahrenheit? So if I was going to put that in Kelvin, I would take the Celsius temperature, 40.3 degrees Celsius, add 273 to that, and I end up with 313 Kelvin. If I wanted to change that to Fahrenheit, I would take 1.8 times the Celsius temperature, and then take that whole number, add 32. So I end up with 104.5 degrees Fahrenheit, which is a really, really high temperature for the UK. I mean, obviously, it's the highest ever recorded in the UK. Maybe here in Texas, that's not like the highest we've ever seen. I think I saw 108 degrees this week alone. But in the UK, 104.5 is a significantly high temperature. All right, well, that was the metric system, that was dimensional analysis, that was density and temperature scales. And I hope to see you guys next time for the moles. Bye, guys.